Throughout this chapter, I've been telling you that the only thing that will affect the rate constant is the temperature. Well, we're finally to the section where we talk about that. So we're going to look at how the rate constant is affected by the temperature. Now, in general, we'll find that as temperature increases, the rate increases, and as temperature increases, the rate constant will also increase. Over here on the right side, we've got an example of a reaction that is increased by increasing temperature. On the left, we've got a glow stick that is put into hot water, and you see that it's glowing extra bright. And then if we take an exact identical glow stick and put it into cold water, you'll see that it is glowing not quite as bright. Well, the reason for that is that the reaction is going faster at higher temperature. So we want to see how much faster. We want to see how does the rate constant change as we change the temperature. So we will see that the rate constant is temperature dependent, and we've been saying that throughout this chapter. We'll see that as molecules move faster, there are more collisions, and with more collisions, that will give us more reactions more effective reactions. Interestingly, we'll find that rate constants tend to double approximately with every 10 degrees Celsius rise. So you'll see that as we go up here every 10 degrees, it approximately doubles. It's a little bit more than double, but it's approximately doubles. Okay. Now we need to go back and look at the collision model a little bit before we move on. In the collision model, we'll find that collisions cause bonds to break. And when those bonds break, new bonds can form. We'll find that in order for the bonds to break, the molecules have to have enough energy and they need to have the correct orientation. So over here on the right, I've got a cartoon that demonstrates what this looks like. So here we've got a reaction, and this is an effective reaction. The molecules run into each other, and because the two atoms that are going to form a new bond hit each other, it's possible for the reaction to occur. When this other molecule is turned around the other direction, we'll find that when the green molecule runs into it, we do not get an effective reaction, and there is no net reaction. So even though these may have had enough energy, no reaction occurs. So what this chapter is all about is does it have enough energy and does it have the correct orientation? The energy part we can figure out pretty easily using math. The orientation part, we kind of have to use a fudge factor to take care of that. And I'll show you that fudge factor here in just a bit. We want to look at something that we call the activation energy. The activation energy is simply the amount of energy that is required for a reaction to take place. We use the abbreviation E sub A as activation energy. And we'll find that the molecules need to have at least that amount of energy, the activation energy, in order for a reaction to occur. Now, as an analogy, and this is an incomplete and not perfect analogy, so don't try to take this too far. But as an analogy, here we've got a golfer, and the golfer wants to hit the ball into the cup. Well, in order to hit it into the cup, she's going to have to hit it up over the hill. And if you've ever played putt-putt or miniature golf or any of those kinds of things, you know that if you hit the ball too lightly, it'll roll up the hill and roll right back down. And that's because it doesn't have enough energy. So none of the balls that you tap really lightly are going to get up over the hill. Well, none of the molecules that are going too slow are going to be able to react. So the molecules must have that minimum amount of energy. Well, now we want to look at something that we refer to as a reaction coordinate diagram. I will say reaction coordinate diagrams are extremely important. We'll see them in this class, but we'll see them extensively in organic chemistry and any additional chemistry classes that you might take in the future. The way that a reaction coordinate diagram works is that it provides us a visualization of how the reaction is occurring. So it provides a visualization of how the reaction is occurring. And it shows the progress of the reaction and the energy as we go through the reaction. On the x-axis, we have what is called the reaction coordinate. In this book, it calls it reaction progress or reaction, reaction progress, I think is the term that it uses. The reaction coordinate, or again, the reaction progress, tells us how far from reactant to product that we have. Over the course of this reaction, we need to break this bond between carbon and nitrogen, and we need to make a new bond between these two carbons. Well, when we break that bond between carbon and nitrogen, here at this beginning point on the x-axis is when we have reactant. Over here at the end point on this x-axis is where we have the product. And in between is somewhere physically in between. Is the bond partially broken, completely broken, or partially formed? So this tells us where we are in the course of the reaction for each individual molecule. On the y-axis, we have the energy. The lower the energy is, the more stable. The higher the energy, the less stable. So the things that you need to be able to identify on a reaction coordinate diagram include the reactants and the products. So here's the energy of the reactants, there's the energy of the products, and so that's where they are. You need to be able to identify the activation energy, which is the difference between the energy of the reactant and the energy of the transition state. The transition state is this maximum energy here. So that is our transition state energy. The transition state species is the chemical that exists at that transition state. It's going to be very unstable, and it's not going to last very long. So, you know, the amount of time that it's actually in this configuration is going to be a very, very short period of time. So we call that the transition state species, and in some textbooks it will refer to it as the activated complex. We want to be able to identify if a reaction is endothermic or exothermic. In this particular one, the energy of the reactant is higher than the energy of the product, so the energy is going down. That amount of energy, the delta E, is going to be released probably as heat into the surroundings. I don't know if you guys remember this, but delta E and delta H are approximately the same value, and in this case they should be almost exactly the same value. We will find that the rate will depend on the size of that activation energy. The bigger the activation energy is, the slower the reaction is going to be, because it's a bigger mountain that you have to get over. The smaller the activation energy, the faster the reaction will go. Now, to determine how many molecules have enough potential energy, enough energy to get up over that activation energy, can be given to us by what we refer to as a Maxwell-Boltzmann distribution. Maxwell-Boltzmann distributions tell us the distribution of energies of molecules in a sample. We will find that the molecules in a sample have a wide distribution of energies. That distribution is represented by this curve. The higher the curve is, the larger the fraction of molecules that have that particular energy. So for example, on this blue line, you'll see that the blue line is very close to the origin here. So that means there's not very many molecules that are moving very, very slowly in this sample. The vast majority of the molecules are moving much faster than that. And so we'll find that some of the molecules are moving slowly, some of them are moving much faster, and so have much higher kinetic energies, and that some fraction of the molecules will have energy that's greater than this dotted line. And that dotted line represents the activation energy. So any molecules that have more energy than the activation energy will have the potential to react. Doesn't mean they will react, it just means they have the potential to react. Well, we will find we will find that the area of the shaded area under the curve is going to be proportional to the rate constant. So as the temperature increases, we will find that the curve will flatten and broaden so that we have more molecules that have more energy than that minimum amount of energy, the activation energy, and so we have more molecules that are capable of reacting. Again, it doesn't guarantee that they will react because we still have the orientation factor to consider. But we will find that the shaded area will be proportional to the rate, and in fact, it'll be proportional to the rate constant. We can mathematically describe what that shaded area is using this function. This function comes from doing a little bit of calculus, and thanks to Maxwell and Boltzmann, we can determine what that value is. So the fraction of molecules that has at least that amount of energy will be equal to negative EA over R, or E, which is the base of the natural log, raised to the negative EA over RT, where EA is the activation energy, R is the gas constant, and T is the temperature in Kelvin. So we'll find that as the temperature increases, this fraction will get larger. So it turns out that the rate constant K is proportional to that fraction. So we can say that the rate constant K multiplied by a frequency factor, that frequency factor is sort of the ultimate fudge factor. It takes care of the orientation issue, how many molecules are actually oriented in the correct direction when they run into each other, and it also takes into account other issues that make it so that all the math works out. So it's really a big fudge factor, but we don't worry about it because it gets sorted away without much of an issue. We'll replace that f with the function we saw on the previous page, and so now we get this. Well, this is called the Arrhenius equation, and the Arrhenius equation is an absolutely marvelous equation that gives us a relationship between our rate constant K, the temperature, and the activation energy. It's a really, really useful equation. What we want to do is we want to take this and turn it into a linear equation. And we want to see how does the rate constant change as a function of temperature. So let's do that. We're going to turn this into a linear equation. So to modify the Arrhenius equation to turn it into a linear equation, we are going to take this Arrhenius equation and take the natural log of both sides. If we take the natural log of K, of course, we'll just get natural log of K. Natural log of a product is going to be equal to the sum of the natural logs of those components of the product. So natural log of A times the natural log of this component is going to be equal, or natural log of A times this is going to be equal to the natural log of A plus the natural log of this. So we can separate those two parts of that expression. Well, natural log of A, we're just going to leave that alone. But the second part, where we have the natural log of E raised to the negative EA over RT, well, E is the base of the natural log. So the exponential function and the natural log function are inverse functions, meaning that natural log of E to this, we're just going to take the part that is the exponent here, and we will get this. All right, so that gives us the natural log of K is equal to the natural log of A plus negative EA over RT. When we rearrange that a little bit, we will get natural log of K is equal to negative EA over R times 1 over T plus the natural log of A. And as we have a desire often to take really complicated looking equations and turn them into linear equations, well, that's what we've done here. So if we plot natural log of K on the y-axis and 1 over the temperature on the x-axis, then we should get a straight line. And the slope of that straight line is going to be equal to negative EA over R. That's pretty cool. All right, so what we want to do is, what can we do with this equation? Like, what useful can we do with this equation? All right, well, here we have done multiple experiments where we measure the rate constant at different temperatures. Once we've done that, where we've measured the rate constant at different temperatures, we can then plot natural log of the rate constant K on the y-axis, and on the x-axis we'll plot 1 over the temperature. And of course that temperature needs to be in Kelvin for this to work. When you do that, you get a straight line. What's great about this is that this works regardless of what kind of equation you have. It could be first order, second order, fifth order, it doesn't really matter. But what's important is that it always gives a straight line, and that straight line, the slope, is equal to negative EA over R. So if you take the negative of that slope and then multiply by R, you will get the activation energy for that reaction. And that is a very cool result. All right, so that's a very cool result. Now, the downside of doing this kind of experiment, as you can see, you have to do what, 1, 2, 3, 4 different experiments, maybe 5, maybe 6, who knows, and plot them on a graph. It takes a lot of work to do this kind of data set. But it is possible to take a shortcut. Right? It is possible to take a shortcut just by looking at any 2 points on that curve. Now, you probably remember way back in algebra the formula for the slope. Well, the formula for the slope, usually we use the letter m for the slope. Formula for slope is y2 minus y1 over x2 minus x1. And you'll see that that's what we have here, y2 minus y1 over x2 minus x1, and that's equal to m. Well, going back to that previous page, you'll see that the value of x is equal to 1 over t, the value of y is the natural log of k, and the value of m, the slope, is equal to negative EA over R. Well, if we take those values and put them into that formula, where if we have like y2 and y1, that would be natural log of k2 and natural log of k1. So we can take this equation, substitute those values in, and we get this. So negative EA over R is equal to the slope, natural log of K2, that's Y2, natural log of K1, that's Y1, X2 is 1 over T2, and X1 is 1 over T1. Okay, now we're going to take this and cross multiply it. So we're going to take the negative EA over R and multiply it by this. We're not going to expand that. We're not going to multiply it out or anything. We're just going to leave it in that form. There is one little trick that I want to do, and that one little trick is that we're going to multiply both sides of this equation by negative 1. What that does is it gets rid of the negative sign here in front of EA. So it will get rid of that negative sign. In addition to that, it will make it so that this negative natural log of K1 becomes positive, and the natural log of K2 becomes negative. So these two will switch places. So here we've multiplied by negative 1. You can see what happened. So we got rid of the negative and we switched the places of these two. Now there's one last little thing that we can do. If you have the difference between two logs, so log of K, natural log of K1 minus natural log of K2, we can rewrite that as the log of the ratios. So we can rewrite that as natural log of K1 over K2 is equal to EA over R times 1 over T2 minus 1 over T1. At first glance, this does not look like a very simple equation. And in all fairness, it is not a very simple equation. It is a little bit complicated. However, it is simple algebra from this point to look at this and see that there's one constant, a true constant, r. That's a universal constant. And then there are 5 variables. With those 5 variables, if we know 4 of them, we can get the 5th. And so that's what I want you to be able to do, is if you know any 4 of those variables, you could get the 5th. Now, typically the variables we will look for will either be the rate constant K or the activation energy EA. And so we are now going to look at number 53 and 54 and solve that. All right. Well, previously I wrote down this equation on our page here so that we don't have to rewrite it. So there is our equation. We've got a first order reaction with a rate constant of 2.75 times 10 to the negative 2. There are the units. At 20 degrees Celsius, what is the value of K at 60 degrees Celsius if the EA is equal to 75.5 kilojoules per mole? All right, well, this is a pretty straightforward problem. We've got our equilibrium, our rate constant K, equilibrium constant, spoiler alert, it's coming up in the next chapter. Our rate constant K, we're going to call that one K1, and we're going to solve for K2. Now, sometimes I find it useful to go ahead and just list all of the values that you know and what you're looking for. So we know that K1 is 2.75 times 10 to the negative 2. So we know that's K1. K2 is what we're looking for. Temperature 1 is equal to 20 degrees Celsius. And 20 degrees Celsius is equal to 293 Kelvin. Temperature 2 is equal to 60 degrees Celsius. And 60 degrees Celsius is 60 plus 273, so 333 Kelvin. And then EA is equal to 75.5. And then finally, we also need R. And I'm going to write R up over here. So R is equal to 8.314 joules per mole Kelvin. If you're wondering, is that different than the number that we usually use? It is a little bit different. So previously we had used the rate, we had used this 0.0821 as our rate our gas constant, and we're using the 8.314 joules per mole Kelvin. That 8.314 is just in different units. It's the same constant, but in different units. So 8.314. Okay, so now let's put those values in. So we'll put natural log of 2.75 times 10 to the negative 2 over K2, and that's equal to EA over R. Well, EA is 75.5 kilojoules. I'm going to go ahead and turn that into joules, because you'll notice that our gas constant is 8.314 joules per mole Kelvin. So I'm going to put 75,500 joules per mole. All right, and then R is 8.314 joules per mole Kelvin. And then, so the joules per mole are going to cancel out, and now our Kelvin will cancel out when we do the temperature here. So 1 over T2, and T2 was 333 Kelvin, minus 1 over T1, and T1 was 293 Kelvin. So 293 Kelvin. All right, so now we've got just a mathematical quantity. Let's go ahead and solve that quantity. So in order to do that, make sure my calculator is here on the screen. So in order to do that, we're just going to punch all the numbers in. I think what I'll do is, okay, this will be pretty easy. So I'll do 75,500 divided by 8.314, and we get a number, and that's the quantity here. We're going to multiply that by this difference. So 1 over 333, I'm going to put 333 to the negative 1, that's the same as saying 1 over, minus 293 raised to the negative 1, and then close parentheses. And that's going to give us the value equal to negative 3.723. We probably don't have that many sig figs, but we'll just run with it. So 3.723, so negative 3.723. So now we have natural log of 2.75 times 10 to the negative 2 over K2 is equal to negative 3.723. Well, we want to solve for this thing that is inside of that logarithm parentheses. And in order to do that, we need to do the inverse function. And so the inverse function is the anti-log or the inverse log. And so for natural log, it's the e to the x button. So if we take the inverse log of the logarithm, we're going to get 2.75 times 10 to the negative 2 over K2. And that's equal to e to the negative 3.723. All right. And now we're just going to divide both sides by this and multiply both sides by K2, and we will get this, that K2 is equal to 2.75 times 10 to the negative 2 over e to the negative 3.723. All right, and now we can get that value. So 2.75 times 10 to the negative 2 divided by e. Let's see if we can delete that. All right, yes, so second of the natural log. So e to the negative 3.723, close parentheses. And that gives us, we'll just call it 1.14. All right, the units for that are going to be the same as the units for our other one, so it will be seconds to the minus 1, since it is a first order constant. Okay, now we're going to do the same thing for this one. The only thing that is different, all of these quantities are the same. K1 is the same, T1 and T2 are the same. The only thing that's different is EA. So we just have to get to here. We just have to get to here and put in that new value for EA. So natural log of 2.75 times 10 to the negative 2 over K2 is equal to 105 kilojoules is 105,000 joules per mole. And then R is 8.314 joules per mole Kelvin. And then 1 over 333 Kelvin minus 1 over 293 Kelvin. That's a 9 there. Okay, so again, we're going to do this quantity, 105,000 divided by 8.314. And then we're going to multiply that by 333 raised to the negative 1 minus 293 raised to the negative 1 and close parentheses. And that's going to give us negative 5.178. So negative 5.178. All right, so natural log of 2.75 times 10 to the negative 2 over K2 is equal to negative 5.178. We're going to take the antilog of both sides, and that will give us 2.75 times 10 to the negative 2 over K2 is equal to e to the negative 5.178. So now we'll just switch the place of those two quantities, and we'll get K2 is equal to 2.75 times 10 to the negative 2 over e to the negative 5.178. All right. So 2.75 times 10 to the negative 2, and then we'll divide that by the inverse log negative 5.178, close parentheses, and here we get, looks like 4.88. All right, so 4.88 seconds to the minus 1. On my key, I had 4.87. I don't know if I punched something in different or whatever, but yeah, close enough. So 4.88 seconds to the negative 1. All right, so that is an example of how to calculate K1 or K2. So the next thing that we want to do is we want to look at an example so that instead of calculating K, where we calculate the activation energy EA. All right, well, you'll notice I paused the recording for a moment just so I could write down that equation and then write down these variables. And so now what we want to do, so there's K1, K2. Now what we want to do is we want to figure out what each of these variables are. So let's look at the problem. Understanding the high temperature behavior of nitrogen oxides is essential for controlling pollution generated in automobile engines. The decomposition of nitric oxide to N2 and O2 is second order with a rate constant of this and this at so this at this temperature and this at this temperature. So we're going to call that K1 and T1, K2 and T2. So we're going to write down those numbers. So K1 is 0.0796 molar to the minus 1, seconds to the minus 1. Again, it is a second order, but you can use this on second order. And then we'll do 0.0815 molar to the minus 1, seconds to the minus 1. T1 is 737 degrees Celsius, which we need to convert that into Kelvin. So 737 plus 273, and that gives us 1010 Kelvin. And then for T2, it's 947 degrees Celsius, and 947 plus 273 equals 1220. All right, now that we have those quantities, we can put them into the equation and then solve for EA. So we'll do natural log, and then K1 is 0.0796, and then 0.0815. So that's K1 and K2 is equal to EA over 8.314 joules per mole Kelvin. And I'm going to put that in there as joules per mole Kelvin. The Kelvin are going to cancel out here, but the joules per mole will end up sticking around. So now we're going to get 1 over T2, and T2 was equal to 1220 Kelvin. And 1 over T1, 1010 Kelvin. Okay, So now we've got this, which we can just evaluate that by punching it into our calculator, and then we can evaluate this portion. So we'll take this difference and then divide by 8.314, and that will give us a number that we multiply by EA. So let me show you how all this works. So natural log of 0.0796 divided by 0.0815. All right, so the left side of the equation came out to negative 0.023, we'll call it 2359. We probably don't need that many sig figs, but we'll round at the end. All right, so we get that. And then EA, and so now we'll do this quantity. So 1220 raised to the negative 1 minus 1010 raised to the negative 1 is that quantity. And then we're going to divide that by 8.314. And that gives us negative 2.050 times 10 to the negative 5. Okay, so now EA is going to be equal to negative 0.02359, and this part is negative 2.050 times 10 to the negative 5. All right, so negative 0.02359 divided by negative 2.050, second EE, negative 5. All right, and that gives us 1,150. We're just going to call it that. We have 3 sig figs in this, so 1,150 joules per mole. We could call that 1.15 times 10 to the 3 joules per mole. And that is our value for EA. Okay, well, I'm going to stop this video, and then in the next part of the video, we're going to be looking at reaction mechanisms.